So one way of saying what a vector is that it's like a two-dimensional number would be a good way to say it. Yeah, I don't know if you've ever seen it or not. You could try. It's just a weird angle. And ultimately, maybe we'll have you switch them. But for now, yeah. So most numbers convey only one figure, one number's worth of data. But a vector will communicate to you two pieces of information. Like I said, it's a two-dimensional number. Or at least that's what we'll say they are right now. In a couple days, we'll also talk about three-dimensional vectors. And in general, you could have like a 10th-dimensional vector or something like that. Right? There's nothing wrong with adding more commas and putting more components in there. And those are what those things are called. A and B are the two components of the vector. And there are lots of ways to write vectors. One way that we'll many times go to is this like angle bracket. Method. Parentheses are actually fine too. I mean, people do that too if it's clear from the context that we're talking about a vector. The way we might picture a vector is by using a directed line segment. And the key word here is segment. This is not, I don't know, if you were in geometry class, you would think, oh, array. No, it's not really an array, because here, this arrowhead doesn't convey this goes on forever. It conveys the direction, but the actual length of the vector as we've drawn it is important. And so, like I said, we depict it by a directed line segment is how you might say it, where A and B are the horizontal and vertical components that we just listed up above. And of course, the other way to name a vector, to give the same information instead of component form, would be to give it in terms of its magnitude and direction, which you've probably heard maybe before. Oh, a vector is a thing that has magnitude and direction. So let me give you a quick example of that. Say I'm here, and I want to give you directions for how to get from where I am to the file cabinet. And the way to do that would be to say, there are two ways I could give that information. The first way would be to say, go 15, it's 15 feet to the right and 15 feet up. Wouldn't that tell you where the filing cabinet is with respect to where I am? 15 feet that way, 15 feet that way. The other way, though, I could tell you is that it's 15 root 2 feet at 45 degrees. And both of those tell you exactly where the filing cabinet is relative to me. Right? They both tell you where that is. So that's us kind of giving either way here. Both are useful and common. Two vectors, I'd mentioned the zero vector here, whatever, it's fine, 0, 0. Two vectors are equal up to translation, right? So if I know we've pictured it here, and we often do picture a vector in its standard position, that is like with its tail at the origin. But there's no reason it has to be there. If it's been translated somewhere else, then we still consider that the same vector. Right? So if I step over this way a little bit and give the same vector, 15, 15, that's still the same vector. But now it gives me instructions instead of like how to get from B to A, so you need a file cabinet. So same components and same magnitude. Note that it's not, doesn't matter where it is though. Its position in the plane doesn't matter. Now you know what a vector is. It's the fastest you've ever been confused. Yeah. A vector is a two-dimensional number. There you go. That's the summary of this slide. I mean, right away, I think it is a little confusing, partially, only, not because this is like hard to understand, but because you're like, okay, fine, I'm like with you, but like why would you ever want to consider such constructs? And so I think it's helpful to right away have a few examples of where these things come up. So we're going to name this kind of number a scalar, and that is a number that has, like the numbers you've always worked with all your life, we just haven't given a name to them, are called scalars. That is one-dimensional things. All of these quantities that you'll encounter, you don't have to write them all down, please. But I just want to give you a couple examples. Like for example, if I want to communicate the mass of the table, all I have to do is deliver to you one number, and you know everything there is to know about the mass of this table. So that's called a scalar, and I'll explain why that's called a scalar later in this lesson. But vector quantities, which maybe you're a little less familiar with, you do recognize when I name what those things are measured. And I think in particular, velocity is one you've heard lots of people kind of harp on, right? Like, you know, even earlier on in your life, people were like, well, velocity and speed are not the same thing. Right? Well, now we can finally have that discussion. The people who say that velocity and speed are not the same thing are correct. Right? Technically, by speed, we mean a one-number figure that captures the magnitude of the velocity. But the velocity, technically, is to be communicated together with its direction, magnitude and direction. And in fact, all of these quantities are meant to be communicated. It's not really the force if you just tell me the magnitude of the force. It's technically only the force if you give me a vector quantity for the force. Take it as you will. Anyway, don't get too caught up in these. Just know that now you know that these are all like actually pretty common things that we want to think about in math and especially in physics that contain vectors. And anyone who's done, I don't know, anyone who's been in physics yet has used vectors already and can already tell you and testify. Yes, we use vectors all the time. Or I don't know, you do free body diagrams and POE and stuff too, right? Resolve forces and things. Those are vectors. Those are vectors. So, I'm not going to give you the time to write down every word on there, but
see, I told you.
We now encounter the multimedia part of our lesson. Here we go.
I'm applying for a new villain loan. Go by the name of Vector. And it's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you have not. Do you want a demonstration? Oh, ah! It's so difficult sometimes to get blood inside.
There you go. Now we can see, we can watch all these other minions and Despicable Me. What?
You didn't stay for the free
Oh, yeah. That's, I know. There's so much more to be fun to watch, but I stopped with the part that talked about the math, and I liked it where it done. But really, it's kind of, the life, really, there's a life lesson in vectors, right? It's not just about effort, it's about direction. It's like what, you can apply yourself, but you also need to apply yourself in the right direction, boys and girls. There's your motivational speech for today. All right, so this is kind of a cute name for this, but the head minus tail rule is actually kind of helpful in understanding how you might build a vector from 2 points. So literally by head, we mean like the arrowhead. You take the arrowhead end, whatever point coordinates that has, minus the coordinates of the tail. That's what this says in math here. And notice that the vector AB we might denote like this. AB says the vector from point A to point B, where B is the head, and A is the place where it originates from, the tail. So when you're ready, let's use the HMT rule, the head minus tail rule. We're going from R to S to take these 2 points and construct for ourselves the vector from R to S. So this is weird because we're taking a vector from R that goes and then points to the origin instead. Right? It's a little weird. It's okay. So what is S minus R? What do we get here when we write the vector? 0 minus negative 20 is positive 20. And 0 minus 10. Hey, good choice. Alright, go to class. Alright. Yo, what do we have? Comma what? Yeah, so we're doing S minus R here. Hopefully that's okay. Yeah, it's a little weird. Let me picture that in my head here. So RS is the vector from 20 from negative 2010 up to 0 to 0, 0. So it points like that. If you were to translate it to the origin, you might call it this, but regardless of where it is, you'd call it this. So apparently, we're saying that these are equal. So RS, the back vector, and PQ are the same vector. So, well, what's PQ? Well, PQ is, of course, Q minus P. Well, we weren't given Q. That's a problem. Let's name Q temporarily. Give me 2 of your favorite letters. What would you like? No, first give me 2 letters. Any letters you like. JP. Okay, perfect. Okay. And we're, yeah, you have a question though too?
Yeah, why do you use pointing parentheses?
Yeah, so, and we can relax this a little bit, but technically, yeah, and I guess this should say that up here too. Maybe. Is that what you're wondering about? Like when we say it's a vector, we might want to make it clear that it's a vector or something rather than a point. But we'll be a little flexible about that. I'm not too concerned. Yeah, so these are kind of we're thinking about as points. And this is like a vector, 20, negative 10. All right, we'll use J and P here. So what is the vector from P to Q? Well, Q minus P would be what? Yeah, J minus 3. Apparently this is the same vector we're talking about over there too. And P minus 4. I think in a second you'll be able to tell me what J and P are, all right? I mean, if J minus 3 is the same thing as 20, since they have to have equal components, then in a second you'll know. So, figure it out. Tell your neighbor what. Tell your neighbor what you got. All right. Well, so what did you get here for the the coordinates of Q? 23 and negative 6. Yeah. So if Q has that coordinate, then the vector from R to S and the vector from P to Q are the same, and we'll say that they're equal, even though, I mean, you might be picturing them in your head right now as being in different locations. The vector from R to S, like we said, might be pictured over here. But this is my head is the origin. It's like here, right? It's like pointing up to the origin from down, or negative 2010 down to the origin. This one is pointing from 3, 4 to 23, negative 6. 4 to negative 20 to 23, negative 6. So it's like over here, right? So it's the same vector by translation, but and that's okay. Those are the same vector, is what we're saying. They have the same component form. 20, negative 10 is the component form of both RS and PQ. Magnitude and direction, yes. We got to talk about how to find those things, but I don't think I need to tell you, really. I have it up here, but what is the magnitude of a vector? Of course, it's really just the length of the vector, and that can be gotten by Lulu's famous theorem. Yeah, this is just the Pythagorean theorem, so I don't think I have to tell you that the magnitude of a vector is, of course, the square root of a squared plus b squared. It's just a triangle, friends. So you could call it the length. Because these vectors typically represent things like force, things like that, it's a little weird to call it the length of your force. That's a little weird. But magnitude of your force, that sounds a little better. Sometimes people call it the norm as well. We'll probably mostly use the word magnitude, but sometimes people call it the norm as well. And it's denoted by this very familiar piece of notation. What does it look like? Yeah. Now, you might be thinking, that's a little frustrating that like we're overloading this notation. It means 2 things now? Well, in some sense, no. It's actually a beautiful notation, and they are the same thing actually. When you were first introduced to absolute value, do you remember this being the way at least someone might have said it to you at one point in your life? Like, what's the absolute value of negative 10? Well, it's the distance that you are away from 0. Yes? And the answer, of course, is 10. But isn't that what we really want to capture with the absolute value is our distance away from 0? And that's exactly what we mean by the magnitude here too. And in fact, go with me for a second. If you consider like what the magnitude of like say there's only one component of a one-dimensional vector, no one would ever do this. But let's say they did, you would get only like one component here, right? And you know that the square root of a squared is the same thing as the absolute value of a. Isn't that what we mean? Like if you plug, this is as good as But you don't need the absolute value function in your life. You just need this function, right? If you plug -10 into this function, you do get 10, right? This is, and by the way, let's go to the third dimension already right now too. How would you find, what do you think the magnitude formula is in the third dimension? Yeah.
The cube root of a cube plus b cube plus c cube.
Not quite. Not quite. And now you have to work it out. Maybe it's not as obvious as I thought. If you had a C component though, anyone else want to take a guess? I don't know, maybe I should make you prove it. It's not too hard to prove. A little picture of a rectangular prism and draw some triangles, calculate the length of the diagonal of the box. Well, we'll leave that a mystery for now. Okay, that's fine. But two-dimensional, it makes sense. It's just a Pythagorean theorem. Okay, so what about the angle? Well, of course, the angle can be gotten using trig, right? So I'll say here that, of course, the angle is the angle that has a cosine of a over the, it's just what? It's just a, the horizontal component, divided by the hypotenuse, right? It's like, and a sine of the vertical component divided by the hypotenuse. Or if you wanted to say it's the angle that has a tangent of b over a, you could say that too, whatever, you know, whatever. The point is just, you know, use your trig knowledge here. I think I could have given you this question without having really said any of this up here, and you would have been fine, right? Find the length of this and the angle of this. Right? Go ahead and do it. Well, the magnitude is quick. You may need a calculator to calculate the angle, though. Right. So, what is the magnitude? Walk us through that here. How do we calculate the magnitude? Josh, where are you? Take us through the magnitude. What do you get there for the magnitude? Root 80 is a good answer, yeah? Or, you know, we can just leave it that way, I guess. You could also say, I guess, what would that be? 4. Yeah, 4 root 5 actually works. I think you can pull a 16 in there. Oh, whichever, whatever. It's fine. All right, now go to the calculator and do your calculations, but I also want to hear what you're actually typing in. We're trying to figure out what the angle is here. I want to know which arc trig function you're getting. Which quadrant needs your angle be in? Your angle needs to be in what quadrant? Yeah, quadrant 4. So whatever you get, make sure that the answer you're reporting is quadrant 4, right? It's because the vector lies in quadrant 4. Or, so use your calculator. It doesn't specify. You can give it to radians, degrees. You can give me a positive or a negative angle.
Yeah.
All right, so what are you typing in? What are you typing in your calculator, someone, Elizabeth? What are you typing in your calculator?
Sorry. Right now, I'm taking in inverse cosine of 6 over root 5.
Okay, inverse cosine of, oh, I see, yeah, 4 over 4 root 5, or 1 over root 5. I'm with you, okay. I'll write down what you said. And what do you get there?
$1.107.
1.107. 7 sounds like radians to me, which is fine, I guess. Of course, that's not quite right, though, because, so what do we have to do? You mean negate? Yeah, so I think that's a fine answer. We could maybe give 3 sig figs or something. Negative 1.11 or something, radians. Some of you had it in degrees. What is it in degrees, just so other people can check? Negative 60. Negative 63.4. Negative 63.4 if you like. Did anyone have a trig function that got this for you? An arc trig function that got this for you right away, so you didn't have to adjust it afterward by negating it. What did you use? Yeah, in that fact, actually, inverse sine or inverse tangent will work, right? So what would that be? Inverse tangent of what? Yeah, inverse tangent of negative 2. If you type that in, you'll get the same answer right away without any adjustment. So whatever. The point is, in the end, just get it right. You know, like if you're in the wrong quadrant, that's fine. Just use some geometry and trigonometry to like get you to the angle that you know you need to say. And in fact, you know you have to do that kind of adjustment if you end up in the third quadrant, right? There's just no arc trig function that gets you that immediately. So you know, there are certain times when you'll have to do that. We should box our answer. All right, good. Well, the other way is not too bad, right? What if I give you instead the magnitude and direction, and you need to figure out the components? Is that a thing we can do? Say I have these red things given in the problem. Say I can tell you that the vector is so many units long and is at such and such an angle with the positive x-axis. Well, the things, of course, we seek are this blue and this green length, and then we'll be done. And that's a little right triangle, so we can apply right triangle trig. Anyone know right away, like, what the blue, the length of the little blue component is? How would you get that? Yeah, there's a cosine involved. That's true. Say it again, Paul. Yeah, cosine theta times the magnitude. Does this sound right? Something like that. And then what about the blue, or the green now? Anyone else? Yeah, magnitude of this vector times the sine of the angle. Right? These two things should be familiar to you at this point, perhaps, right? This is a point on a circle, if you like, this point out here, of radius magnitude v, right? If we were on the unit circle, then the blue and the green would be cosine theta and sine theta. There's lots of ways to see this. If we're talking about a triangle that isn't a right triangle, remember how you calculate the height when we're doing ambiguous case or whatever? It's this side length times the sine of the angle. Oh, we've done this before. Okay. But yeah, I mean, once we make that realization, I mean, it's just very easy to write down immediately what the component form of a vector is. This is the easier, probably the easier direction to go in than the last problem. This is the easier direction for sure. So even without a calculator, let's take a second to do that problem and tell your neighbor what you get. Figure out what the cosine and sine of 120 are. A little speed trig on the fly here, but you got to know these, right? What's the cosine of 120 class? Negative a half, good. And sine is?
It's positive.
True.
And it's root 3 over 2.
Hey, you know something, good job. Yay. We quickly remember. All right, so we have a final answer. Is this what you told your neighbor? Negative 26, comma 26 root 3. Is that what you told your neighbor? There we go. See, I can't give you another problem that's any more interesting than that. Even if we had a messy angle, it'd be okay. You could just use your calculator, cosine, sines, multiply by the magnitudes. All right, the next thing to say something about is to say something about vector addition and scalar multiplication. The two operations that happen in exactly the way you would probably guess they do, even if I didn't have this slide in the presentation. How do you think you add two vectors together? What would you like to do? Yeah, add the individual components? Correct. That is in fact what we do. So there you go. Component-wise, add the two components of the two vectors together. Visually, this makes sense too, right? So here's, say, vector u, and when we add vector v, we get vector u plus v, which is this. And it's pretty clear that this is the correct way to do this addition if this is the vector we seek. Because think about for example, the horizontal component of u plus v. Isn't that clearly the horizontal component of u plus v? Isn't that clearly the sum of the horizontal components from the blue u and the green v vector? This component from blue, this component from green, together they add up to the whole horizontal component of u plus v. And the same argument can be applied about the vertical components and how they add up. If you want to do u minus v, you might do u and then go in the opposite direction for v. There's u minus v. Just subtract the components, I guess you could say. It's also worth mentioning that that this kind of addition, this vector addition, is commutative. And that's pretty clear really from two perspectives. One is the algebraic perspective. What's v plus u, the vector v plus the vector u? Well, it'd be the same thing except v1 plus u1 in here. And you know the property of the real numbers, and that's what we're using here, is that will be the same thing as u1 plus v1. So this is commutative. It also commutes in the picture, doesn't it? What if we do v plus u? Do we get the same vector as a result? U plus v? Oh yeah, we do. We arrive at the same place. So there's a visual way to see that too. The thing you're looking at right now, of course, is a parallelogram, right? Okay. The reason we also sometimes call this the resultant is because, like, if you and your friend are applying some force on some object, you might say, what's the resultant force? Like, what force results from us taking our forces and combining them on this object? And the answer is another vector, which is the sum of those two force vectors. We'll do a lot with that kind of stuff in the coming days. The other operation that's very easy to define, because I think it's exactly the thing you would expect to do, is what do you think happens when you multiply a vector by a number? Well, of course, you just multiply each component by that number, right? So this is called scalar multiplication. And so now we can maybe finally say why we use the word scalar for numbers, like numbers that you've always used in your life. Because what does it do? What effect does it have on a vector when you multiply it by that vector? It does what? Yeah, it scales that vector, doesn't it? So it has, that scalar is a good name maybe. In fact, let's be more clear. How could you get it to lengthen the vector? What property of k would you have to, what would k have to be if it lengthens the vector? Something greater than 1, yeah. Could you shrink a vector by multiplying by an appropriate k? What would k have to be?
Yeah, it has to be less than 1.
Very good. And what about could you do, what else could you do with k? You could make it 0, and then it would be like collapse the vector completely. What else could you make it? Yeah. How would you make it flip? Yeah. Yeah, some negative k value will make it flip. So you can either lengthen, if k is greater than 1, you could shrink the vector and make it shorter if the k is less than 1, or you could flip it the other way. It looks like here k is negative 1 maybe, right? But k could be like, you could do both at once, right? You could k be negative 1/2, and then multiplying that by your vector will flip your vector in the opposite direction and shrink it by a factor. So these are things that make sense to us in 1 dimension. They should make sense to us in 2 dimensions too. The pictures are really what get us here on this, right? These make sense. So no huge surprises, I think, on this slide. So now, try using these operations in succession and just playing around with them a little bit on this slide. I'll call on a couple people in a second. Some of these are easy, some of these are not so easy. I've got a couple things happening on some of these, right? Scalar is just a number, right? So without too much fanfare, Stephanie, you want to give us the answers out the first one right away? You can just shout it out. Very good. So the first one's not too bad. All right, now they get a little more interesting. I'll give you a second. It's longer.
For the absolute value, does it answer the positive?
Well, it's not the absolute value. It's what's our new word for this? Huh? Well, yeah. I mean, it'll always be a positive number, but we call it the what today? Yeah, the magnitude. The magnitude of this vector. Fong, do you have the inside vector here? What vector are we taking the magnitude of here? What is 3a minus b? And then we'll also say what the magnitude is. But agree, class? That's what. Okay, so that's the thing we're going to take the magnitude of. And do you want to say what the magnitude of that is? 9. And wait, you didn't labor using the formula to figure that out? It's just like, let me back to you. The square root of negative 9 squared plus 0 squared. 81. Oh wait, maybe you don't need the formula. Maybe it's just a vector pointing this way 9 units, and if someone asks me, how far away is that from the origin, I can just say 9. Right? I can just use my visual on this. Maybe you don't need a formula for that. Okay, well whatever. The answer is 9, of course. So on this first one, you get a vector answer. On this second one, we have a scalar as our answer. And can you take the last one, Zach? Okay. You there yet? What's the magnitude of b? Do you have that yet? Anyone have the magnitude of b yet? What is that? Root 45, someone yes?
Yes.
Okay. Root 45, I hear someone say. And what's b plus 2a? Let's say what that is here. B plus 2a is, say it again? Negative 11, 10? Okay. So, by the way, 45, can we do that?
Well, you can take the 3 out, or you can take a 3 out. 3
Yeah.
or 5.
Yeah, so we could say, I guess final answer maybe negative 33 root 5, comma 30 root 5. Is that a good way to write it? I don't know. And so our answer here is a vector, a scalar. Here it's a vector. And even before you did these problems, I think you can see that this is going to be a vector, this is going to be a scalar, this is going to be a vector right away. That might be where we have to end. I have one more slide, but I guess I can't talk about it. I'll show it to you briefly, but you're going to be so confused on the homework tonight. It's okay. I think it'll be all right. The unit vector, when they ask for a unit vector, they just mean a vector that's 1 unit long. So scale it so that it's 1 unit long. All right, well, we'll have to wrap it up there for now. And homework 1 on your homework sheet for tonight, please. Homework 1. Oh, I should have called on Mitai.
You should have. Oh my god.
He's got a vow of silence today, if you can believe it.
I'll send it.
Bye, guys. Have a great day. Do your-
Hallelujah.